everyone, and welcome to another episode of That's Absurd. Please elaborate. They've asked us to stop. They've begged us to stop, but we just keep making podcasts.
We sure do.
We can't be stopped.
We can't be.
So,
Wow. It's absurd.
Heaven is my witness so long as I have a microphone. You'll have to pry it from my cold, white, cis-het male hands.
Congratulations on all of those things. Because I've heard that men don't feel appreciated. So there you go. Congratulations on
I think we'd be appreciated more if we stopped. But anyway, I'm Julian. I'm one of the two science communicator hosts of this show.
And I'm Trace Dominguez, the other science communicator host of this show. If this is your first time listening, we take questions from you, the audience, and we do our best to give you a satisfying answer. The only thing we ask is those questions be absolutely ridiculous or far out or wild or one might say absurd.
Yeah. Oh, hey, look at that. It's in the show title.
Yeah.
That's a good point. I hadn't thought of that. Well. So, Trace.
Yeah.
You're kicking us off this week. Who's your question from and what did they ask?
Oh, my question is from Win, who asks, could we be Martians? Until scientists became a buzzkill, sci-fi shows and movies had Mars as the obvious place for aliens. So my question is, could we be Martians? Yeah, well, I think that's great.
I mean, I've heard that men are from Mars, so half of us, right? Half of us are Martian.
We're really doing the science nerd version of the manosphere today, aren't we? Just right here in the first few minutes. We've congratulated men for existing. And now we're buying into the pseudoscience of men are from Mars and women are from Venus. When really all humans are from Earth.
Yeah. Now, after we've migrated from our respective planets somehow.
Wynn does have one more line that I've left out of their question. If the Earth, as is, was where Mars is now, would life have evolved?
Oh, fun.
And what would the differences be?
Oh, okay.
Which I think is actually the more interesting part of the question. So could we be Martians is sort of like the headline, I guess. And so the answer is, could we be? I guess, like if we wanted to, like we go there and we build a house, I'm now a Martian. In the same way, if I go to Virginia, I'm now a Virginian. You know, like, sure, yeah, I guess.
Yeah, I kind of love the different approach to it. I mean, I thought could we be Martians is like, did at some point we come from Mars or something and settle
okay,
here?
I'll get into that a little bit.
Yeah.
How long do you think we've been using the term Martian? Because I looked this up because I was curious. Like, how many hundreds of years has the term Martian existed? And I gave you a big hint there.
Yeah, shot in the dark. I feel like it's about one.
It's way more.
I mean, more?
Used in the way that you're thinking of, like, to describe an alien who lives on Mars, you're correct. That's only a little more than one. But the word Martian, as in pertaining to Mars, has existed since, like, the 14th century, which I thought was kind of neat. I'd never really thought about it that way, because when you say Martian, I think a modern 21st century human says, like a person from Earth is an Earther or a Terran, depending on what sci-fi network you're trying to pay attention to. And then a Martian is a person from Mars, or an alien, I guess, from Mars.
Yeah.
Which I thought was kind of neat. And as an astronomy show host on PBS, I have to tell you that Mars has been visible since antiquity. It actually is currently visible in the night sky. And ancient Greeks called planets wandering stars because it's a bright red dot that you can see very clearly, but it moves faster than the stars way farther away and behind it. So they would call them wandering stars, which is, where the word planet came from, I guess. Mm-hmm. And the first person to see Mars through a telescope, any guesses which bay? We know which bay.
I mean, it's got to be Galileo. It's
exactly.
Yeah,
Galileo
the guy
Galilei.
who invented the telescope.
Right.
Like looking
Can
at
you imagine
an obvious feature of the night sky. Yeah, that's got to be it.
Could you imagine if there were no telescopes and no one had ever looked like at any of the stars, moon, anything up close? And then,
there was a time when that was true.
Right, 1608. And then in 1609, Galileo's like, how excited would you be to just like, for the first time ever, be like, oh my God, I can see it up close.
I'm a little jealous of people living in times where there were like complete paradigm shifting revelations, like the low hanging fruit that we could observe so easily. Just like, oh, I took these lenses that were made for glasses originally, and I just kind of put them in a line in a tube. And now I can look at that wandering and, oh, what? Oh, it's not like anything else that I see at all.
Yeah. If I pointed at Betelgeuse, which is also kind of reddish orange, that seems just like still a little teeny dot. But if I pointed at this slightly brighter dot, it's a completely different thing. Oh, it's like a big round thing.
And that big round thing has like little small round things around it, like its own like moons. Oh my gosh, I've changed our entire perception of the universe.
Wow.
Took me 5 minutes.
And over time, I'm going to look at it again and again, and I'm going to see changes in the polar ice caps on it. Yeah. And the greenish gray splotches and dark brown rusty things are going to change because the planet is moving and rotating. And then there are clouds sometimes. This is all stuff that was observed into like the 19th century, basically.
You just don't get that stuff anymore, you know?
No.
Like the last thing I can think of was when Hubble in like 1927 realized that the Milky Way was not the only galaxy and an entire universe existed beyond it. And that's, for me, like the last major shift I can think of in like our conception of the universe.
The confirmation of the first exoplanet, I would say, is a minor version of that. Like they discovered the first exoplanets, like imaged them in the 90s or something. But then they first confirmed them in like the early 2000s. And they were like, okay, we know for a fact that there are planets around other stars. We thought there were, but now we know there are. And like that, I think that's a minor version of this, but you're right. There hasn't in our life. The best we've got is I can use this giant cloud server farm to make my favorite actor punch a robot. And I'm just like, this is not a paradigm shift. This is trash. You have invented expensive garbage.
Thanks.
Anyway, moving on. So anyway, we've known about Mars forever. We've been looking at Mars for a long time. Mars is very far away. Yeah, we're talking about Mars. So the question that Wynn is asking is, if the Earth was where Mars is now, would life have evolved? And so first we have to really understand the habitable zone. So the habitable zone is the power of a star is going to determine how close or far away a planetary body can orbit said star and still contain liquid water, which we call the habitable zone because it's very important to us as a type of life that needs a lot of water in order to not look like a raisin. And so basically, it's the total radiant heat power emitted from a surface proportional to the fourth power of its absolute temperature. And that's the Stephen Boltzmann law, basically to find the power output of a star. And it determines the range around a star where a body could be warm enough for liquid water to exist on the surface. So for us, Earth is pretty close to the inner boundary of that, and Mars is pretty close to the outer boundary of that. But both are in, technically, the habitable zone of our star, which is pretty cool to think about. So I think now that we understand the habitable zone, we need to understand why if there are two planets in the habitable zone, one has water and one very much, well, at least liquid water does not. And for that, we need the magnetosphere.
Yay, the magnetosphere.
The unsung hero of planet Earth.
Truly.
I don't think anybody thinks about the magnetosphere. Everybody talks about all sorts of other things, atmospheres and the sun and plants and oceans and snow and, all this other stuff. Without the magnetosphere, none of that. We got none of that. It is the most important part of our atmosphere. This is our Star Trek shields up. Yeah. It's the thing that keeps us from dying terribly.
Kiss everything that keeps us habitable goodbye.
Right. So let's explain what the magnetosphere is. It's a magnetic shield that is generated by our spinning solid core in our molten middle core, if you will, or like mantle area. So that the core is spinning, and as it spins, it's literally like a battery almost generating a magnetic field around the planet.
Right.
Now, this magnetic field is what stops the solar wind, which are charged particles coming out of the sun, literally charged bits of matter or coming out, or energy coming off the sun, and it keeps our atmosphere from being stripped away by these polarized particles. Without it, we would look more like Mars. Mars does not have a magnetosphere because its core got cold and stopped spinning.
Loser.
This is why we think it could have had water in the past because maybe it did have a spinning core and did have a little Mars magnetosphere, a cute little one, because it's about half our size. But it cooled off and now doesn't got one no mo. So without the magnetosphere, we don't have an atmosphere, and thus we don't have anything, really. As the six-fingered man once said, if you don't have your magnetosphere, you don't have anything.
Great. All right. And now we will use that clip from The Princess Bride for an Instagram reel.
For no reason at all. Not because our last Princess Bride clip
we're going to just keep going to that
obscenely
well.
viral.
Sabrina,
one
you
could
know what
call
to
it
do?
the pit of despair. I read some things about the magnetosphere that I thought would be neat. Based on what I've said so far, do you know a lot more about it other than what I've just said?
I mean, I'm currently taking a class on electricity and magnetism, and it does come up like a little bit tangentially.
Yeah.
But all I really know is, like you mentioned, when you've got current flowing, you're going to generate a magnetic field, basically.
Right.
And the ball of iron at the center of the Earth has a lot of current flowing. And even then, the magnetic field is quite weak, compared to other magnetic phenomena that you are used to, right? Like a bar magnet is much, much stronger than the magnetic field, which is measured in Tesla, right? And I don't remember the figure off the top of my head, but I think the Earth's magnetic field is like micro Tesla. It's very, very small, but still, powerful enough to deflect charged particles from the sun, which is how you get the aurora borealises at the poles, right? That's the charged particles being funneled to the poles and exciting the atmosphere and giving off light, which is cool. It is cool. And it's also useful for navigation, for like wildlife, or for airplanes.
The compass.
Yeah.
Okay, stop talking about airplanes.
Anyways, I'm glad we got
your
to
quota.
The topic we all want to hear me talk about. Anyway, so I'm fine. I will stop.
Your favorite podcast within a podcast. Julian talks airplanes. So anyway, the magnetic shield, all of that is correct. It is, I don't know also the Tesla level of it, but it's quite minor. It's enough that it can pull a compass needle, right? Because that's where magnetic north is. But it's not so much that we're worried about like a magnet that you just have sitting on a frictionless surface moving around, the planet. Interestingly, though, it is quite large and it encompasses not just Earth, but it gets so big that it can stretch out past the moon. So the astronauts that just went on Artemis 2 went around the back of the moon. They were still within our magnetosphere, which is pretty amazing to think about. So what happens is it's sort of like a big teardrop shape because it would be, like a bar magnet. It would make like that kind of, fruit shape where you have it looks kind of like an apple almost.
Yeah.
But instead, what ends up happening is it shapes into like a teardrop, almost like a comet, because the solar wind is pushing it away from the planet. So it's constantly compressed in the front. Yeah, flavor blasted, exactly. And so it's compressed about 6 to 10 times the radius of the Earth in quote unquote front of us, between us and the sun. And then behind us, it's like 60 Earth radii out into space, which is pretty cool. So this is all to say we have a magnetosphere on Earth, which is important. That's why we don't look like Mars. And then we're in the habitable zone still, even if we go to the Mars side. So if we can keep both of those, there's no reason that we wouldn't be able to, at least on basic level, maintain some of our atmosphere and thus some of our liquid water, theoretically. The next most important thing we have to think of is Mars is frickin' far away.
Is it?
Really, really far. Like at its closest, it's a 9-month journey in a really fast spaceship.
Yeah.
Like it took us 3 days to get to the moon. And that thing was booking it.
That's also a quirk of orbital mechanics, though, that 9-month time frame.
True.
Because you're basically doing like another big circle to meet Mars where it's gonna be at its closest point. It's not a straight shot.
No. If you took a straight line, though, it's still quite far. In fact, it's so far, I think it's actually easier to think about it in terms of the sun's irradiance energy. Okay. So the sun is very, 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 very unimaginably, just unfathomably large.
I have heard that, yeah. Mm-hmm.
Yeah, we've talked about it on the show before. However, it's actually easier to think of it in this case as a single point. So the sun is one spot in space, and energy leaves the surface of the sun and spreads in every direction out from the sun. So imagine Julian and I are two photons, and we're on the surface of the sun. What's up, Julian? How you doing?
Hey, bud.
Here on the surface of the sun.
You hang out here often? Nice to get to the surface after bouncing around for 10,000 years inside,
I've been trying to get to the surface for so long,
I keep getting lost.
So
I'm asking for directions.
You did? Oh,
Yeah.
I never asked for directions, man. Why would you do that? Anyway, now we're next to each other here on the surface of the sun. Where are you heading? Where are you heading? Where are you heading?
I think I'm going to go that way.
Great, straight line. Cool, me too, me too. So we'll be like parallel for a while.
Yeah,
cool,
yeah.
That sounds fun.
Yeah,
that
you
sounds
want
fun.
to run parallel for a little bit? Yeah,
here we go,
let's do
here
it.
we go, here we go. Pew! And then fast forward 10, 20 minutes, and we are not anywhere near each other anymore in space.
We drifted
because
apart.
of just the fact that, the sun is a ball. And so even though we're close to each other for a little while, the further away you get, the less actual photonic material there are, the less energy there is in that part of space.
We're more spread out.
Everything that comes out of the sun spreads out over distance. And because of that, we have to calculate the irradiance energy of the sun, because further away from the sun we go, the less light is going to fall upon our planet. And that's bad. And it is a calculable thing. It's pi over 4 pi r squared, where pi is the power and r is where we are in the orbit. So think of like a sphere coming out of the sun. If Julian and I, the two little photon bros, are right next to each other on the surface of the sun, by the time we get out there, we could be millions of kilometers apart. And again, somebody could calculate that. I didn't. This is called the solar constant. And we've calculated this for the average orbits of all the different planets. But essentially, Earth is at 1 AU. So we get 1,360 watts per square meter, or about 174 petawatts of light across the planet.
Yeah.
Mars is at 1.5 AU. So for every meter that our photon bros travel, Julian's, let's say, is heading toward Mars and I'm heading toward Earth. Julian's going to travel to 3 meters, or have to go 3 meters for every 2 meters that I travel. It's just 50% more travel time. And irradiance scales at 1 over the distance squared.
So squared.
It's an inverse square law. Yeah.
Right.
So the solar constant, also known in the math as Ks, or K sub S, if you're writing it down. The Ks for Earth, again, 1,360 watts per square meter. Mars is only 590 watts per square meter. Much less.
A lot less energy to work with, yeah.
It is actually easier to assume in this case that planets are flat disks and not spheres, because you don't want to calculate the atmosphere is bouncing some of it away near the poles, and in the middle it's absorbing a lot more, and all of this stuff.
And it's at an angle at the poles.
And it's at an angle, and we wobble,
yeah,
and all sorts of things. I just want to point out, though, we are not a flat disk. We just had an iPhone video of Earth set around the moon. Every space agency in the world, even the ones that hate each other, have all confirmed that we are not a flat disk flying through space.
Trace, come back
and
to me.
apparently NASA employees are the only ones screwing the wall, but they keep getting their budgets cut, and no one has any photos of the wall.
You okay? You okay, bud?
I'm fine.
Okay.
I'm fine.
All right.
Fine. If they had people stationed on the wall like the Night Watch, who wouldn't want that cool ass job?
It would be
Where's
a cool
the job posting for that? You need millions of people.
Yeah.
It's a big planet.
And at the edge of it, the biggest it could be, and it's who's going
It'd be
to turn all those
humongous.
boats back?
Who's going to turn and we've got not a single photo of it. Everyone has a photo machine in their pocket, and we don't have a single photo from anyone anywhere on the planet. Anywhere.
Yeah.
Anyway.
Or no
matter.
ships have been turned back, they got close, and it's the wall watch was like, hey.
You can GPS track every ship in the world on websites for free, and people aren't like, oh, here it is turning around because it got too close to the wall.
Yeah. Nope. Anyway.
So 590 watts per meter squared is what we've calculated for what Mars is getting from the sun. If we can maintain our magnetosphere, if we can maintain our water on our surface, well, then we could have Martian life. The thing is, it's not even purely 590 watts per meter squared, because we also have to talk about albedo. One of my favorite things, because people never think about it.
Yeah.
Albedo is the reflectance of a planet. So like the moon has an okay albedo. It's actually pretty low, surprisingly, but it reflects the sunlight back at us and we get moonlight, which is really just reflected sunlight, but that's fine. Mars doesn't have much of an atmosphere right now, and it doesn't have much cloud cover, but it is a rusty red. And so it reflects about 16% of the energy that hits it. So of that 590 watts per square meter, some of it's being reflected just back into space, just like a mirror.
Yeah.
Earth does have an atmosphere, has a lot of clouds, also has the light-colored places like snow, water, greenery, and it's reflecting about 30% of the energy hitting it. So we're getting even less energy than that. But with all of those things, we have everything we need to do basically what is just a simple calculation. We've got the Stephen-Boltzmann constant, which is that, again, total energy radiated per unit of an area of a black body, which is a perfectly absorbing body. We have our Earth-Sun distance, and we have what that would mean for our planet. Now, I do want to point out, the National Center for Atmospheric Research did use this calculation to determine the average temperature of Earth, just from math.
Yeah.
Earth's expected temperature is the fourth root of the solar constant times 1 minus the albedo of Earth over 4 times the Stephen-Boltzmann constant. So basically everything we've talked about so far, you put it into a single equation, and you can get the average temperature of a body orbiting at that spot. This is useful for any number of planets, but also other stars. Now, I know you didn't just do that math in your head, Julian, so I'm going to tell you, this gets us a total temperature for Earth, on average, of about negative 3.1 Fahrenheit or negative 19.5 Celsius.
You know, I feel like the Earth is warmer than that, though.
Is it?
Yeah.
Are you sure?
I don't feel like every day I'm well below freezing.
What?
Yeah.
You're right.
Thank you.
You're right.
I feel like there's something not included in the calculation.
I can't gaslight you on this one. Our actual average is 14 Celsius, 57 Fahrenheit. So I hear you saying, Julian, why Earth so cold? Earth not cold that.
Earth, yeah. Earth warm than that. Earth much warm than that.
Do you know why?
Sure do. Do you want me to say it?
Please.
The greenhouse effect, baby.
Heck yeah. So we know the average temperature of Earth because we live on it. It's not negative 20 Celsius. And that 30 Celsius difference, that 60 Fahrenheit difference is entirely due to our atmosphere. That's, again, why the magnetosphere is so important. Not just so that we don't die of DNA damage, but it keeps our atmosphere here. And without it, we would not be able to be warm. But we can't just add 30 Celsius or 60 Fahrenheit to our Mars temperature, because if we do this calculation of the fourth root solar constant times 1 minus the albedo of Earth over the Stephen-Boltzmann constant for Mars's solar constant of 590 watts per square meter, not great, Bob.
Yeah, still
not great.
Much colder.
Negative 67 Celsius.
Oh, no,
negative
not
88 Fahrenheit. So even if we added 30 Celsius, we're still negative 37 Celsius as our average surface temperature. Our oceans would not be liquid.
It's still like Antarctica temperature.
It is cold.
Like in the winter.
It is so cold. And this holds, though, even though Earth is bigger than Mars, and so you would think, oh, we're getting more light. There's less light in space at that spot. And so, yes, we're bigger, but we're not going to get so much more that it's going to be that much warmer.
Yeah, and we're dealing with light over an area anyway, so it doesn't really matter.
The math is extremely complicated. I could tell you exactly what it would be. And yes, it would probably be more than what Mars gets just because of our size. But at the same time, we're reflecting more. We're in a different spot. We're a larger planet. You know, there's a lot of different things that I just didn't think people wanted to hear me do some math on the podcast any more than we've already done. So can we then warm up the Earth? Right? Can we then do that? Sure, we're doing it now. It's not awesome. But we would have to do this if we wanted to be Martians, like in ancient times. So in an ancient Earth, before life arrives, sure, it's possible that we could have had these like 4.5 billion years ago, early photosynthetic microorganisms were spewing methane out prior to the great oxygenation event in about 2.5 billion years ago, a little more. That methane event was warming the planet. So we could have done that if Earth just happened to be at that spot instead. Of course, then maybe Theia would have missed us because that's pretty far, and thus we wouldn't have a moon, and thus we wouldn't have volcanic activity because our moon is so large, so it keeps our core hot, and then we have a magnetosphere. So again, all of these things matter. And I'm not a paleogeological historical expert on what would happen. I'm not a planetary geologist. I'm not going to be able to tell you that like the balance of methane, CO2, and O2 with an inert nitrogen in an atmosphere at Mars level, we would have to have this much more of it. You can do all that math.
Mm-hmm.
The likelihood of us getting that with the planet we have is very low. So long story short, Win, a lot of things would have had to happen perfectly for us to be Earthers. And many of those would be even more unlikely to happen because of where we are in our solar system, because of how much light we're getting, how much heat we're getting. When that happens, we get heat that allows some life to do something that completely changes how our planet operates, like those cyanobacteria that gave us oxygen 2.7 billion years ago, or the methane spewing photosynthetic microorganisms from almost 4.5 billion years ago. All of those things had to happen, and had to happen for a long time, in order for us to be able to get here, have enough nitrogen, enough CO2 to keep us warm, enough oxygen to breathe without having too much to constantly cause fires and reactions with all of the stuff in our world. And it's just a very unlikely combination. Now, if you were to just like hit a button and move Earth to where Mars is, we would freeze. We would be a snowball. So we would have to evolve a thicker atmosphere, more methane, more CO2. Something would have to change for us to be able to survive at Mars orbit. And it's tempting to think, wow, we're so lucky, which is true. We are.
Yeah.
We're very lucky that this happened, that we got to be here.
Yeah, I love existing. I'm a big fan of it.
Super fan.
I am not doing anything better with my time. So
I feel like if I was going to be a fan of something, number one fan, existing. After that, I can be like sort of minor fans of everything.
I'm also a big fan that you exist. So
hey, thanks, man.
Yeah.
Love your brain. Love your brain.
Love your brain.
I think that a lot of people like to think of this as like, I'm an elf on a shelf waiting for a planet that shows up, right? We are not lucky enough to have an environment that supports us, because we wouldn't exist in any other environment. We only exist because this environment happened and we evolved to exist in it.
Yeah, we exist the way we do.
This is what we do. We didn't do anything else. It wasn't like we were a blank slate sitting somewhere waiting for a planet that we were like, oh, I can live there. Nah.
It reminds me of that one comic where there's like a bunch of bed bugs sitting around before the invention of a bed. And then one bursts through the door and they're like, you'll never believe what just happened. Somebody invented beds and they're like, finally.
That's great. So you mentioned before, could we have been Martians and then come here, right?
Yeah, that was my interpretation.
So there are a bunch of theories of life. And I think it would be neat to think about if Mars could have those, or how we got them. So could we be Martian? Sure. But why do we have Earth? And the one you're mentioning, of course, is panspermia, which I think is one of the biggest theories. I think it's a really good theory.
It's fun.
Do you want to explain what panspermia is?
The idea basically is that life on Earth originated outside of Earth, like it hitched a ride here on like a comet or an asteroid or something, and seeded Earth basically from somewhere else. And so that would mean that life on Earth doesn't all just have a common ancestor with each other, but possibly with some extraterrestrial life as well.
Yeah. And there's lots of evidence that organic molecules and materials exist in other places around the places we've explored. They're looking for them on Mars. They think they exist in places like warm places like Io, or in the oceans of Enceladus and, all of these places. But they have to go find them. They still haven't.
That's what Europa Clipper's on its way to go try and do.
Exactly.
Which is very exciting.
It is super exciting. And bacteria and life, based on experiments we've done where they like put it on the ISS and just expose it to space, and then they're like, it's still around, still alive, made it.
Yep.
And they do that. They found bacteria on the outside of the ISS. They've sent probes to the moon and then, gotten parts of them back, and they have bacteria on the outside of them, and they're living, often by accident. They accidentally contaminated them. They do have a whole office at NASA that's called I think it's the Earth Protection Office or something. And
Planetary Defense Initiative.
Planetary Defense, something. And
some
it's just
awesome name.
It's a great name for basically we disinfect.
We're the biggest
We're
germaphobes in the solar system.
We have the disinfectant wipes, and we just wipe off every spacecraft before it leaves the planet.
Oh, planetary defense is more about making sure we don't get hit by like a comet or asteroid.
Oh,
or something.
got it.
Yeah, my bad. Anyway,
Planetary Protection Office.
Something
is,
else.
I think, what it is. But the problem with the theory of panspermia is that it's theoretically plausible for microbes to travel through space, but we've never seen it happen. We've seen a lot of meteorites, and none of them seem to have any, microbe fossils, nothing. And the problem with the theory is that it doesn't solve life's origin. It just moves it somewhere else that we can't get to. They're like, no, it came from over there.
Yeah.
And now it's here.
Where did life on Earth? You asked where life on Earth came from. You didn't ask me where life came from.
Right, exactly.
Technically, I answered your question. And it's like, what are you, our podcast?
You're right. If someone asks about panspermia, you already know the answer. Another theory that life started by being sparked by lightning, which I think is pretty cool.
I love that.
That one's a really good one.
Where they've done experiments, right, where they put like primordial earth ingredients in a bottle and then just like hit it with lightning, and after a while they're like, oh look, there's amino acids. Like, how cool is that?
It's so good. There was a 2024 study where they found, quote, cloud to ground lightning strikes, especially volcano produced ones, awesome, could have created the necessary ingredients for life more efficiently than panspermia or cloud to cloud lightning strikes. Thanks, nerds.
I love it.
Love that. Again, still no evidence that it has happened, but intriguing that it could.
Yeah.
Then there's the primordial soup hypothesis, which is just like all the ingredients existed in a pool of water somewhere, and it just happened to fit together.
Yep.
But there's no real catalyst there, and so it seems unlikely. There's like the lightning or some kind of heat, which is where we get the hydrothermal vents is another theory of life, because the biochemistry is there and it adds the heat to it. That means that maybe that heat can encourage them to react. The newest one, which I had not heard about much, which I think is very cool, is the RNA world hypothesis. Are you familiar with this one?
No, is that a theme park?
It's a theme park. You can ride the RNA roller coaster.
It's the roller coasters all have one rail, and the other wheel is just flopping around out in the breeze.
And then
it's terrifying.
The cars hit each other, and then they rip other people out of the other cars. I think is how it works.
It's a safety nightmare. It's in Florida, so
so they don't care.
They got away with it.
It's fine.
Tell me more about the RNA world.
So the RNA world hypothesis, RNA is simpler than DNA. DNA is quite complex. DNA codes RNA, but also requires RNA to get made. And so they're like, wait, maybe RNA is like the base molecule and DNA is a complex version that RNA kind of got together and somehow made, which I think is cool. But you need proteins to make RNA, and DNA codes those proteins. And so it's just like, it gets complicated and a little chicken and eggy.
I was going to say,
it's cool.
Way better chicken or egg question. Like, which came first, the DNA or the
RNA or DNA? Yeah, I know. That's the nerdy version of the chicken and the egg.
Way better. Chicken and egg is old hat.
Yeah, for sure. I also like the RNA world because viruses are basically RNA in a trench coat. So it's like...
Yeah, literally. Yeah.
Like, why not? Sure, cool. The con of that theory, by the way, is it's just as unlikely that RNA formed as any other organic molecule. So it's like, well, I mean, it could. So could we be Martians win? Sure, maybe we could have. We could have evolved on Mars. We could have panspermed over here back when Mars had a magnetosphere and a better atmosphere and some liquid water. There's no evidence of that. But there are people looking into it. It could have been a volcano lightning situation here on Earth, and if we flipped the switch and moved Earth to that spot, we would just be a frozen snowball. If we evolved in that spot with a thicker atmosphere, still had our magnetosphere, it's possible, maybe, that we could have Martianed, but it's pretty unlikely because it's just so much colder there. Even though it's technically in the habitable zone, we'd need some real Earth remodel in order to make it work. No matter what, though, we're lucky, and this is amazing. And just think, all of those lucky things happened all along those billions of years and lots of billions of little bits of life just so that we could sit here and make a podcast.
The entire history of the Earth was just for this moment.
Look, it worked for Bill and Ted, okay?
Excellent.
On that note, let's take a break and come back with Julian's question.
Yay.
Welcome to RNA World! Ding, 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 ding. Do you want to play one of our many games called Name That Amino Acid? The first person who sends us an amino acid by email gets a sticker. I don't know.
Gets a free ticket to RNA World.
Anyway, Julian, what's your question this week?
My question comes from Tyler, who asks, is there a limit to how hot something can get?
Like,
right? Tyler says, hi, guys. I'm a museum educator, and recently, at least when he asked this question to us in 2024, thanks, question randomizer, for picking it. Anyway, recently, as of 2024, I had a child ask me why hot things turn red. I Googled it, but it got me thinking about heat. We have absolute zero, the coldest something can get, but is there a limit to how hot something can get? And if so, what's the hottest thing in the universe? Why are you ruining my jokes, Trace? Trace, I have a joke in here. Trace, my conclusion is the hottest thing is Trace Dominguez, and you ruined it.
Okay, we'll
ruined it. No, it's fine.
We'll cut it out.
Trace is the hot. No, Kyle, leave it in. Trace's egomania has ruined my joke. But anyway, Tyler,
funny.
First of all, thanks for being a museum educator. That's awesome. I love museum educators.
As a former museum educator.
Are you?
Well, I mean, I was when I worked.
Were you?
Oh, God. Okay. You're making fun of me now.
No way, Trace.
You're making fun of me.
No
if I could
way.
find my fife, I'd be fifing right now.
You go fife yourself.
I don't know where my fife is. It's around here somewhere.
Yeah, I love museum educators. They're the best people. I love talking to them. I love asking questions that make them uncomfortable. That's a personal hobby of mine. But I appreciate when they genuinely field questions from the children's and the work that they do. So Tyler, thanks. Trace, what's absolute zero? How do we define it?
0 Kelvin.
Yeah.
It's when atomic motion stops.
Yeah.
So the atoms aren't wiggling no more.
Except no.
Oh.
I mean, you're right. First of all, we should talk about what temperature is, right?
Yeah. Oh, gosh. Here we go. This is the next half hour. Get ready, everybody. Buckle up. Settle in.
It's going to be the very short version,
What is heat? I don't know.
Heat is the transfer of energy, right?
Right.
Thermodynamic energy. But temperature is the measure of the average internal energy of an object, right?
Sure.
Objects have energy even when they're just sitting there, right? The little atoms inside are moving around. Right. They're either, like, if it's a gas, they're bouncing all over the place. But even if they're like a solid or a molecule, right? The individual atoms are vibrating or they're rotating, and all of these are different forms of kinetic energy. And temperature is measuring that. And it's funny you mentioned Boltzmann so much because temperature and energy are related through the Boltzmann constant.
Right.
If you just multiply.
That's so funny.
Yeah. If you multiply temperature by the Boltzmann constant, you get energy. And you mentioned Kelvin. Well, Kelvin was a scale of temperature worked out by Lord Kelvin. And he and his good friend, James Joule, worked a lot on energy. Joules is the unit of energy, and they were all friends with Boltzmann. So all these things, joules for energy and temperature and Kelvin, are related through the Boltzmann constant. So I like to think that these three scientist friends are kind of together in perpetuity, and isn't that nice? Okay, so it stands to reason then that if you cool something down enough, if you take enough energy out of it, eventually all the little particles wiggling around in it will stop. And there's no more motion, right? And now you've reached 0 Kelvin, right?
That's what they used to tell me in school when they said I couldn't sit still. I had to stop moving.
Yeah. Except you can't.
Well, because I have ADHD.
Yes, not you specifically, and also me too. But no. Yeah. No, I mean, like, as a fundamental rule of the universe, you can't completely take all the energy out of a particle.
Oh, okay. Why?
You just accept that. Yeah, of course.
No, sure. Okay.
Right is the correct question, right? Because when Kelvin and Joule were working on these things, we didn't have quantum mechanics yet. We didn't understand the universe at the quantum scale the way that we do now, the way that we formulated in like the early 20th century, right? And that is basically that everything exists really as a wave. We're used to thinking of particles as like little billiard balls, right? Like an electron is a little pea whizzing around like a clump of billiard balls that make up an atom's nucleus, right?
Right.
And that's a nice, simple model that's useful for conceptualizing things, but it's not really accurate. And a more accurate way of understanding this is that everything's a wave. Everything's an excitation of a field of some sort that permeates the whole universe, right? And so electrons aren't little points. They're actually waves moving around. And waves carry energy.
Right. A wave with no energy is not there.
Nothing. It's not there. So for a particle to exist at all, it's a wave, and therefore it has some energy. So you cannot ever actually completely take all the energy out of a particle. Another reason for that, too, is an important part of particle physics is the Heisenberg uncertainty principle, right? And it's this statement that if you know, say, like the position of a particle, the more you know about that position, the less you know about the particle's velocity. Right?
Yeah.
Its momentum.
Or its spin or whatever. Right?
Yeah. So you cannot fully nail down a particle to be completely still and be able to point to it and be like, it's here in this spot. It stopped moving. It's got no energy. There it is. It's impossible based on the math. And math is cool and all, but eventually somebody's got to go and figure out, like, is this really how it works? Can we verify this experimentally? And recently, there have been experiments that do verify that particles, even with, no energy at all, still have some energy.
Cool.
If that makes sense, right? It's called 0-point energy.
Oh,
right?
Wow. That's like very Stargate coded.
Isn't it?
Yeah.
So they have to have some minimum amount of energy to exist. But how do you measure this? This is cool. In 2025, some researchers took a molecule of like 11 atoms and they blew it up.
Like exploded it?
Yes. Specifically, they made it undergo a Coulomb explosion.
Cool.
So Coulomb. Yeah, there you go. So they shot it with a high energy X-ray that removed all the electrons from the atoms that were holding this whole molecule together. And so now all of a sudden you have a bunch of positively charged nuclei near each other, and they don't like that. So they all repel each other and they shoot off in all directions. That's a Coulomb explosion, right?
Sweet.
And then they measured how fast these particles were going as they shot away from each other. And if they had no internal jiggling, right, they should have a certain amount of energy as they repel each other. But when they actually measured it, they found that those energy levels varied. And that demonstrates that, hey, even if they're just sitting there all together in an atom, they're still jiggling back and forth. They still have some additional energy from just existing as particles. And they demonstrated this experimentally, which is pretty clever, pretty cool. Okay, so now that I've wasted a lot of time talking about how absolute zero isn't really things not moving at all, but basically, hand wavily, that's kind of what it is. It's how we define it. Is there any reason there should be an upper limit that you can think of?
I mean, my first thought was like, okay, well, at some point we transition through all the stages of matter and we get to like a plasma, and then we have a superheated plasma. But I've never really thought about what happens after that, because once you get to a plasma, you've essentially done exactly what you're talking about. You've stripped off all of the electrons because there's too much energy, so it's too hot, and they just kind of out of there. And then, but I never really thought about what happens after that.
You could go farther than that, right? And say like, oh, we put so much energy in that even the fundamental particles like protons are tearing themselves apart, right? Into like a quark and gluon soup.
Yeah, I was going to say a particle soup, which is what they think the early universe was like.
Oh, very good. Yes, exactly.
That's the whole point of CERN. It's trying to mimic the early universe.
Exactly. And so you can dump more and more energy into things, and you can break them down, but then you can keep theoretically dumping more energy into stuff. Why should there be an upper limit?
I mean, at some point, this is how science works.
2 hours later. At some point. No, I don't know. I can't think of it.
I don't actually know. I have no idea. I don't know.
Well,
how does that work?
Part of why I chose this question, what I love about it is The question that the aforementioned child, posed to Tyler may actually have the answer in it. And you mentioned it too in your answer when you brought up black body radiation. And I was cracking up that you just kind of skated right by it. And a little thankful because I'm totally like, that's very important to my question. So thank you for not going too deeply into it. But herein may be where we get an upper limit for how hot something can be, right? Because everything that is above absolute zero is emitting electromagnetic radiation.
Right.
Yeah, because it's got some energy. So electrons are moving around. Even the nuclei, the atoms and the molecules, they're moving around. Anytime you have a accelerating charged particle, you generate electromagnetic waves, right? Just that you're jiggling.
Sure, yes.
Yeah, okay. I can go in more detail.
I've been fooled twice already to say yes, and then I didn't actually know what I was talking about.
Well, okay. So I mentioned that particles are just excitations of a field, right? They're waves.
Yeah, right.
So if these particles are jiggling around, they're waves, they cause disturbances in fields, electromagnetic fields. And we perceive these disturbances in electromagnetic fields as electromagnetic waves. And if they're the right sized waves, we can see them, right? They excite the neurons in our eyes and generate a little signal, and we can interpret that visually, right? But there's, of course, a range outside of visible light, above and below it, and where, longer wavelengths are infrared, or bigger than that, they're microwaves or radio waves. And then smaller than visible light, they're ultraviolet or X-rays or gamma rays, right? The wavelengths get very, very, very small. Well, everything is emitting these waves if it's above absolute zero. The thing is, most things that we deal with day to day that are room temperature, most of the waves they're giving off are infrared. So,
right, yeah, because that's in like the heat as we determine it.
That's
I'm putting in big quotes, heat.
That's why we say like, oh, infrared is like seeing heat, and it is, right? It's the waves that are being given off from an object that's above absolute zero, but it's not hot enough to glow red, right?
Right.
But as something gets hotter, it emits more electromagnetic energy at higher frequencies, so shorter wavelengths. And eventually, if it gets hot enough, it will emit electromagnetic waves in a visible range. It'll start to glow red at what's called the Draper point.
Yeah.
Which is about 525 Celsius, 976 Fahrenheit, or 798 Kelvin, which I'm sure Tyler looked this up when he Googled it and got this answer, right? Once something is hot enough, the wavelengths it's giving off just become visible. That's it.
Yeah.
So we can continue this idea forward. Something gets hotter and hotter, the wavelengths that it emits will get shorter and shorter and shorter and shorter. Do you see where I'm going with this?
It really annoys me when blacksmiths in movies hit the thing when it's not emitting light, because that's when it's too cold. You shouldn't be hitting the metal at that point. You're just wasting your energy and your time. You want to hit it when it's like a nice bright orange color. It's about 1600 Fahrenheit. It's a really nice temperature. It molds really well. It hits really well. It's just nice. Feels good. You can really do a lot with that. But once it gets colder and it's like barely emitting any kind of infrared light at all, then you're just hitting cold metal. What are you doing? What are you doing? What are you doing?
Are you yelling at like fake blacksmiths at like Ren fairs or something that are playing pretend?
No, the blacksmiths at Ren fairs know what's up.
Yeah, they do. Right? That's what I'm thinking.
I'm yelling at the movie blacksmiths.
Movie blacksmiths, yeah.
And unfortunately, I just rewatched Iron Man recently, and Iron Man hits like when Tony Stark's in the cave, he's like hitting cold metal. But then when Ivan Vanko is hitting his metal, it's the right temperature, and I'm like, they learned. Good. Somebody in that creative arts department learned that needs to be glowing.
Finally.
Thank goodness.
Yeah.
Anyway, I'm sorry. You're right. So you keep heating up the thing until the wavelengths get shorter and shorter and shorter.
Frequency
and there's
gets
more and more.
higher.
And so then you end up into the gamma radiation, as we call it, which is like the shortest wavelengths that we have and the highest frequencies and the most energies, which is how you get the Hulk, or really in reality kill someone.
And then what?
Don't they just like pile up on each other? Like until the wavelength is so short that it's just like, I don't understand what happens then. I don't know.
You and leading physicists don't know. Because
good.
At a certain point, right, the wavelength gets so short, it becomes Planck scale.
Right. It's immeasurable.
Right.
The Planck scale is like the smallest number we can think of, the smallest thing you can imagine.
Yeah, the smallest, like, meaningful number, right?
Right. So it's a number, but it's also just like, oh my God, there
was a physicist, Max Planck, a German physicist, and he's got a bunch of things named after him because he came up with a constant, Planck's constant, and using other constants like the speed of light and gravity, he was able to work out a bunch of fundamental things about the universe. And one of these things is Planck length, which is 10 to the minus 35 meters.
That's very small.
It's literally unimaginably small. It's take the diameter of a proton, which is already unimaginably small.
Sure.
And multiply it by 10 to the minus 20 power.
Wow.
Yeah.
Wow.
It's insanely small, right? And this is a length that below this length, math just stops working. Like our rules about how the universe functions breaks down. We don't know what happens below these lengths. Okay?
Okay. That's very small.
I've seen it proposed that photon with this wavelength would have so much energy it would collapse into a teeny, teeny, tiny black hole. But we don't know. We honestly don't know. It's too small. But because things that get hot give off... What's so funny?
I imagine some kind of omniscient creator like yelling, just being like, it's too small. It's too small.
What do you mean you want smaller?
What are you doing? It's
the
too
resolution
small.
of the universe.
I can't
go lower.
It's too small. Stop it. I don't know why Jerry Seinfeld has just said it's like, it's too small. I can't do it.
There's no smaller. There's no such thing as smaller.
Stop asking. It doesn't get smaller. Stop
We're
asking.
out of smaller.
We've got large, medium, extra large. We don't have any small.
Extra small, extra small.
Planck small. That's it.
Done. These beauty standards are ridiculous.
I can't imagine an electron with a tiny shirt that said, I went to Planck length and all I got was this t-shirt.
I'm on the Planck diet. I'm Max Planck now.
Oh my God. Planckmaxxing. That's the name of the diet. Oh my God. This episode needs to be called Planckmaxxing, no? Oh my God, I would buy a t-shirt that said Planckmaxxing on it. It would be relevant.
Looks maxing crossed out. Planckmaxxing.
I'm making no discernible changes whatsoever to my life. Okay. Wow.
Right. So as you heat something up, right, the wavelengths of the light that emits get shorter and shorter and shorter, but eventually you're going to hit this limit, as we mathematically understand it, of the Planck length. And then what? We don't know. So we actually have a temperature at this level where things are emitting Planck length wavelengths. The temperature is 10 to the power of 32 Kelvin.
Oh my God.
So unimaginably huge.
I just clenched.
And this, by the way, is Planck temperature. Planck gets everything named after him, right?
Dang it, Planck.
But this is a billion times hotter than the most explosive events that we can possibly observe right now in the universe, which is like gamma ray bursts that happen when stars collapse in the supernova and they shoot out like a beam of gamma rays. It's like ultra high energy, right? This is a billion times more energetic than that.
Wow.
Yeah. Can you think of where this much energy might have existed?
I mean, yeah, the Big Bang.
Exactly. We think that at one point, the entire universe was this hot. It would have happened 10 to the minus 43 seconds after the Big Bang, or one Planck time. Because Planck gets everything named after him.
This is incredible.
But it's a unit of time below which math stops making sense. Anyway, so one Planck time into the existence of the universe was one Planck length across the whole universe. and was at a temperature of Planck temperature.
Yeah.
Had that much energy to it.
And that's as hot as it can get.
That's as hot as, and again, that's as we understand the laws of physics to exist, that's
right.
as hot as it can get. But what happened before that point? Before 10 to the minus 43 seconds into existence? We don't know. Because the laws of the universe break down as we understand them. And that's an important field of physics is how do we explain things before that moment? How do we explain things above this temperature? How do we explain things below this length? It's something
we don't know.
We're still trying to figure out.
It's a box we've drawn in the universe as far as we can go right now.
Yeah. So Tyler, is there a limit to how hot something can get? It's kind of like the answer to, is there a limit to how cold something can get? And it's like, yeah, kind of. We think there is, but not really. Like, we're not sure. Is that satisfying? No. Is that a great answer for, say, like a small child who doesn't understand Planck length when they're at your museum? Probably not.
Hey, mister. Is there a limit to how hot something can get?
Okay, let me tell you about Max Planck. Yeah. So there's a mathematically defined point where things stop working, and that is 10 to the power of 32 Kelvin. But if that's the limit to how hot something can get, how much energy something can have, not necessarily. There are also other contenders for the hottest something can get, depending on, what model you're working with. String theorists would have you believe that the hottest something can get is actually orders of magnitude lower than Planck length, and it has to do with the mathematics of, how strings vibrate. That would set that upper limit. And, there are other approaches too. And CERN is looking for answers on this as well at the Large Hadron Collider. Yeah. So when you talk about how they recreate the conditions of the early universe or, incredibly high energy collisions, right? These are all things that they're probing with these experiments that they are trying to confirm. But for right now, yeah, the hottest things can get, the mathematical limit, 10 to the 32 Kelvin with an asterisk, because maybe things can't get hotter.
There's this really cool hallway at CERN in the visitor area, and its length, they have this like big sticker on the wall, that they've had made, and it's just here at the left end of the hallway is the Big Bang, and then at the right end of the hallway is like where we are now. And it's for a lot of the hallway is just this big orange particle soup that gets slightly less orange as you're walking, and it's just like excellent. And it has a thing that's like CERN's trying to figure out what's going on here.
This little wedge,
which
right
is
at the
great.
beginning.
It's such good SciComm. I loved it so much.
Yeah. God, I love smart people who talk about the things that they're smart about.
Same.
They're so awesome. People like museum educators.
Totally.
Love them. Well, that is going to do it for this week's episode of That's Absurd, Please Elaborate. The show is created, produced, and hosted by the hottest thing in the universe. Oh, there's the joke that Trace ruined. There it is. I had it right there.
Thank you.
Trace
Thanks
Dominguez.
That's very kind of you. It's not even in the remotely close to being true.
Hey, Trace, if you think about it, we're all part of the universe. We were all in some form present at the Big Bang. We were all at some point the hottest thing you could possibly be.
Honestly, that makes me feel much better.
Isn't that
I feel
nice?
much better now.
Isn't that
that
nice
is nice.
thought? I love
we
thinking
are all the hottest thing.
Science says that we're all attractive. We all exert a gravitational pull on our surroundings because we have mass. We're all hot. We're all definitely above absolute zero. We're all emitting heat. And we were all at one point in our youth, the hottest you could possibly be.
Oh, man.
Isn't that nice?
That is nice. I like it. I'm not the hottest thing in the universe. Be our editor who produced and edited this show, our wonderful Kyle Sisk.
Yes, man who has not cooled down since the Big Bang.
The only human man at Planck temperature. Kyle Sisk.
The amount of energy, if you were just anywhere near him, if you were in within, I don't even know, like a galaxy's distance of him. Oh my God, he would blow you to shreds. It'd be incredible. Anyway.
This show was also associate produced by Sabrina Capello. She's normal temperature.
She's normal. She's cool. We
love
like
her. Love her. Normal temperature.
Normal.
Our music is thanks to Epidemic Sound.
Did I give myself credit yet? I also wrote and produced this show.
Yeah. Julian's also involved in the show.
Man with an unquantifiable temperature.
Thank you to the listeners who submitted questions featured in this episode, Wynn and Tyler. If you'd like to submit a question, look for the form in the show notes. You can email us at hello@that'sabsurdshow.com. Visit our website, that'sabsurdshow.com/ask. Call us on the phone at 302-TAPE-SHOW, TAPESHO. We could not do this show without your questions. We have so many of them that I had to vibe code an app to randomly select questions, which we now both use as best as we can so that people don't have recency bias, because there's so many questions and we love all of them.
Special thanks to our Patreon subscribers. They're all great. They went over to patreon.com/that'sabsurdshow and they were like, these two idiots are fun. Here's some real dollar bills. And that is an incredible and unexpected and wonderful thing for you to do. In particular, we'd like to thank our absurd administrators, Adam, Les, Austin, Jonathan, Dan, Sabrina, The Brain, Hannah, Apothecarian, Christina, Atomic Straw, Brian, Shane, and Metric Ton of Batcat. Also, congrats to our bingo card winner, Therese. She's got quad bingo over there.
Wow.
Way to go, Therese. Also, I see a lot of you that are very close to them, and I'm going to give you permission to count Trace's child voice as an accent of dubious quality, and that ought to tick off a couple for you. So
that should be fair. Yeah. It was an accent of dubious quality.
As I'm reading the names, some of these are really funny because they like communicate with us through the names they've picked for their bingo card. Like some of them will have two cards and they'll like apologize. They'll be like, I'm sorry, I lost access to my other card, so I made a new one. And it's like, it's okay, Emily. Like, well, I don't mind. You can have 50 cards in here. That's fine by me. We're not real rules guys over here. In the bingo corner. So
we don't make the rules. The protons, electrons, and neutrons make the rules.
That was established a Planck time after things all got started, and we're just rolling with it ever since.
Leave us a review wherever you're listening right now. The reviews tell other people the show is worth their time, and also tells us that we do a good job, because ultimately we are just a couple of entertainers who we just need our ego soothed.
I crave the validation.
I sure do.
I needs it.
Especially now that you're in school and you're like, did I do good? And the professor's like, yeah, sure, whatever. But then somebody writes, he made me laugh, and you're like, I needed that today. So please leave us a review. It tells other people that the show is worth their time and makes us ugly cry. If you want to see clips from the show and share them with your friends, your networks, go to That's Absurd Show on Instagram or TikTok or YouTube Shorts. We have that as well now. And you can find the show on YouTube as well. A special thanks to those listening on Nebula. Hello, Nebula people. Thanks for listening. By listening to the show, they support this show directly with payments from Nebula that we get because you listen there instead of listening on our public feeds. That's really awesome. Thank you for doing that. Join Nebula at nebula.tv/that'sabsurdshow. They will give you a discount for joining because we're part of Nebula, so you can get an annual subscription for a pretty affordable price. And you can also, again, support all the creators that are there on Nebula. And there are so many creators out there now, so you can watch any of those videos, and by watching it, like you would have anyway, you support the creator, which is pretty awesome.
Well, Trace, what do we say at the end of every episode?
When you change the way you look maxing, it sings. The things you change maxing will also change. This we call Planckmaxxing.
Is that a quote from Max Planck?
It's a real quote from Max Planck. When you change the way you look at things, then the things you look at change.
That's a real that.
Max Planck quote. It is a great quote, but it's better if you say, when you change the way you look maxing, then the things you look at change max.
I mean, if your name is Max, which
this
for him
we call
it was.
Planckmaxxing.
It's true.
It's funny on so many levels. Planckmaxxing.
Is it time for a shirt? Good. Is it time
Is this going to be the first shirt?
First merch?
Maybe it should be. It's so good. It's so funny.
We have to get on it while Looksmaxxing is still a thing. You know the internet moves fast.
Yeah, it won't be. It'll be dated by the time we get it, and that will make it better. Oh my God. So funny. Planckmaxxing is so funny.
I love it.
Well, thanks for listening, everybody. We'll see you in... I mean, I guess I could say a jiffy, but I guess I could also say plank time.
See you plank time.
When you change the way you...
Okay, that's definitely an accent of dubious quality.
I thought of it. I was like, I wasn't going to do an accent, but then I was like, I have to do it.
That definitely counts for their bingo cards.